Multivariable calculus is just calculus, but with more than one variable. For single variable calculus, we performed our operations on functions that looked like y equals f of x, where the function had one input value that generated one output value. We are going to be looking at functions that have more than one input variable. Here's the formal definition. Definition: a function f of two independent variables is a rule that assigns to each ordered pair xy in some set D exactly one real number, f of xy. There's no reason that we have to stop at just two input variables. We could have three or more independent variables, and everything would still work the same. It's just that these are much more difficult to visualize, and so we'll primarily be sticking with two variables. And although we won't discuss it now, you may also want to think about what happens if you have multiple output variables. Just as with single variable functions, we have the concept of the domain of a function. Definition: the domain of a function f is the set of all inputs at which the function is defined. We are going to be using the so-called natural domain of the functions. What this means is that if the function is given as a formula, then unless explicitly told otherwise, the domain is the set of all points for which the function makes sense. The key things to look for are that values under a square root are non-negative, and that the denominators of fractions are not zero. For example, let's determine the domain of the function f of xy equals 1 over x minus y. We want to know the values of x and y that we can plug in and get a meaningful result. We can observe that the fraction makes sense as long as the denominator is not 0. In other words, we need x minus y to be not equal to 0, or y is not equal to x. We are going to draw this domain on the xy plane. We want everything except for the points that lie on the line y equals x. So we will shade in the whole plane except for a dashed line corresponding to the line y equals x. The dashed line is how we indicate that this collection of values is to be removed. This notation is also common when drawing the edge of other boundaries that are excluded, such as circles or rectangles. A slightly more complex example is f of xy equals the square root of 2x minus y plus 1. Here, we need the expression under the square root to be non-negative, so that 2x minus y plus 1 is greater than or equal to 0. In other words, y is less than or equal to 2x plus 1. The graph of that domain looks like this. Notice that we are using a solid line because we want the boundary to be included this time. The important thing here is that you're not trying to memorize any formulas. At this point in your mathematical career, you should be able to recognize when these types of expressions do and do not make sense by just thinking about it. The two big clues to look for are square roots and fractions. You should not take the square root of a negative number, and you should not divide by 0. As with single variable functions, there are multiple ways to represent functions of two variables. One of the first ways we learn to represent a function is by creating a chart of values. But rather than arranging the chart in a single column, it's usually better to make a two-dimensional table when working with a function of two variables. It's important to label the input values so you know which one is which. For reasons that will make sense shortly, the x values are in the vertical direction and they increase going down the page. We can then fill in every position with the number we get from the formula when we plug in the corresponding values. Another way to represent a function is with a graph. There are two input variables and one output variable, so we need to work in 3 dimensions. We will imagine that we've drawn the standard xy axis on a sheet of paper placed on a table with the positive x-axis pointing towards us. Notice that the y-axis would point to the right. We've drawn the xy grid in this picture for emphasis, and you should imagine looking down on the sheet of paper from above and rotating your head a little to get the normal orientation. Then the output function will be the height relative to the table, with positive numbers being above the table and negative numbers below. We will label this with the z-axis. Here is a graph of the function. Some people describe this as kind of like an upside-down bowl. Technically, this is known as a paraboloid. In math, we often call the graph a surface, and you should think of it like the outer surface of a ball or a vase. The surface itself is two-dimensional, meaning that a small piece of the surface looks like a plane, but the whole surface curves its way around in 3 dimensions. There's much more we can say about the geometry, but we'll leave that aside for now and focus on building up some more concepts. An important new element of 3-dimensional geometry is that we have 2 different orientations. In chemistry, this is known as chirality. The idea is that the mirror image of something in 3 dimensions is different from the original. If you've ever used work gloves and put a glove on the wrong hand, you've experienced this phenomenon. The same thing happens with our coordinate axes. There's a right-handed system and a left-handed system. In order for our images to be consistent, it's helpful to stick with the same system. Neither one is inherently better than the other, but the right-handed system is a more natural generalization for us. It's also how we set things up earlier. There are a number of ways to think about this. If you draw the x and y axes in the traditional way and lay the paper down on a table, the z-axis will point up out of the table towards your face. Another way that this is described is that if you point your index finger on your right hand in the positive x direction and your middle finger in the positive y direction, then raising your thumb points in the positive z direction. And yet another way to think about this is that if you think about grabbing the z-axis with your thumb pointing in the positive direction, the direction your fingers curl shows the rotation from the positive x-axis to the positive y-axis. Some students find it helpful to cut off the corner of a box and label the edges to get a physical manipulative to help develop the correct intuition. It will take some time and experience to determine which visualization works best for you. A good exercise is to draw your axes in a random orientation, being sure to note the positive direction, and then randomly label them as either x, y, or z. From this, are you able to determine which direction the remaining positive axis points? Here are a couple examples. Pause the video and give it a try. You should be able to get it with a little bit of thoughtful effort. In the next video, we'll begin to explore some common surfaces and some important formulas.